Okay, so in this example problem, we'll be reviewing Archimedes Principle and how we can use Archimedes Principle to determine the temperature of hot air required for the liftoff of a hot air balloon. So to set up the problem, we have a hot air balloon with hot air inside of it. The hot air has a temperature T, a density ρ, a pressure P, and a mass m. Then we have the balloon material itself, and attached to the hot air balloon we have some load. And there's an open boundary between the hot air and the ambient air having temperature T infinity, density ρ infinity, and pressure P infinity. One of the primary sticking points in this problem is really understanding how the assumptions feed into the solution. So let's go over some of those assumptions. 1, we're assuming we have a static system. 2, we're assuming that the ambient air has a constant density. 3, we're assuming we have a constant gravitational field. 4, we're assuming that we're going to be able to neglect the weight of the balloon material. 5, we're going to assume that the balloon can be modeled as a sphere, just so it's easy to do the volume calculations. 6, we're going to assume that the hot air acts as an ideal gas, and that's going to be important because we'll be using the ideal gas law for that hot air. And 7, we have an open boundary such that the pressure of our hot air is approximately equal to the pressure of our ambient air, which is equal to 1 bar. And let's just unpack that assumption for a second. Since we have a static system and an open boundary, meaning there's no material that isolates the hot air from the ambient air, the only way for us to have a static system with an open boundary is if the pressure of the hot air is approximately equal to the pressure of the ambient air. Now, if these pressures were not equal, then we would have flow from the higher pressure chamber to the lower pressure chamber. So for example, if the pressure of the hot air was higher than the pressure of the ambient air, we'd have flow from the hot air to the ambient air, and we would no longer have a static system. So we must assume that our pressures are approximately equal if we're assuming a static system and an open boundary. And again, we're trying to find the temperature required for liftoff of this hot air balloon. So the knowns here, the diameter of our hot air balloon is 20 meters. The weight of the load, so the weight of this load right here is about 500 pounds. T infinity is 20 degrees Celsius, and ρ infinity is 1.23 kilograms per cubic meter. So the first thing we're going to do in this problem is draw a free body diagram in Z of the hot air balloon. And we really only have 3 forces of note. We have the buoyant force acting on the balloon, we have the weight of the balloon and the hot air within the balloon, and we have the weight of the load acting on the balloon itself. So if we do our Newton's second law in Z positive up, then we can just see that we have FB minus W load is equal to 0, because again, we have a static system, there's no movement yet. However, if we break out each of these terms individually, starting with the weight, we can see that the weight of the balloon material was assumed to be 0. So that weight term could just be described as the weight of the hot air, which we could say is equal to mg. At this point, we want to find another way to express m. So we can express m as equal to the product of the density times the volume. And we know that since we're modeling the hot air balloon as a sphere, we could say our volume is 4/3 pi r cubed. If we then take rho times 4/3 times pi times r cubed times g, because we still have that g from mg, and we simplify, we get that the weight term is equal to rho times pi over 6 times d cubed times g. The second term in our Newton's second law is this W load term. That's just basically a given constant, which is the 500 pounds, and that's approximately equal to 2,224 newtons. The last term in our Newton's second law is our FB, our force due to buoyancy, or buoyant force. And Archimedes' principle is what gives us this buoyant force. And Archimedes' principle says that the buoyant force acting on a submerged three-dimensional object is equal to the weight of the displaced medium. So in this case, the displaced medium is air. So our buoyant force is equal to rho infinity times g times v, where rho infinity is the density of the ambient air, g is the magnitude of gravitational acceleration, and v is the volume of the hot air balloon. So performing the simplifications here, as we did previously with v equal to 4/3 pi r cubed, we can see that the buoyant force is equal to rho infinity g pi over 6 times d cubed. So one point of confusion I often see is people trying to apply Archimedes' principle and the hydrostatic pressure equation to the same object. Note that Archimedes' principle is quite literally the hydrostatic pressure equation integrated along Z. So Archimedes' principle and the hydrostatic pressure equation are basically 2 different forms of the same equation. So you do not apply them both, you just apply one or the other. So in this case, we're applying Archimedes' principle, so we do not apply the hydrostatic pressure equation. Alternatively, we could apply the hydrostatic pressure equation and integrate it over Z, but then we would not apply Archimedes' principle, because again, they are the same equation, just 2 different forms of the same equation. So again, do not apply both equations separately, only use one or the other. We're using Archimedes' principle in this case, so we will not use the hydrostatic pressure equation. So how do we solve for the density of the hot air, rho? Well, we have our 3 sub-equations, and we have our Newton's second law, so we just plug our 3 sub-equations into our Newton's second law and then simplify with some algebra. After the algebraic simplifications, we find that rho is equal to rho infinity minus the quantity 6 times W load over the quantity pi times d cubed times g. And if we plug in our knowns from the first page, we find that rho is equal to 1.1759 kilograms per cubic meter. So what does that mean? That means that we need to heat the hot air in our hot air balloon until it has a density of 1.1759 kilograms per cubic meter for the balloon to just lift off the ground. And now the question is, at what temperature does the air need to be to have a density of 1.1759 kilograms per cubic meter? And we're going to use the ideal gas law for that next. So here we're using the specific gas constant form of the ideal gas law, and that says that P is equal to rho times R hat times T. Now, if we take this ideal gas law and we say that P over the quantity rho times R hat times T is equal to 1, and then we apply the ideal gas law to both the ambient air and the hot air, you can get this equation right here, because essentially this is saying that 1 is equal to 1. So the fundamental assumption here is, again, we have the static system with an open boundary, so the pressure of the hot air is approximately equal to the pressure of the ambient air. So not only can we cancel out these R hats, because again, this is just the specific gas constant of air for both the ambient air and the hot air, it's air in both cases, so this R hat is the same for both. You can cancel out this P and P infinity as well. And after simplifying, what you end up getting is 1 over the quantity rho times T is equal to 1 over the quantity rho infinity times T infinity. And in other words, that's just saying that rho infinity times T infinity is equal to rho times T. Now here, you could see that we know what rho infinity is, we know what T infinity is, and we know what rho is. So the only thing we don't know is T. So solving for T, you can see that T is equal to the quantity rho infinity over rho times T infinity. Plugging in our knowns here and remembering that with the ideal gas law, we must use absolute temperature, so we don't just use the 20 degrees C, we use 20 plus 273.15 to convert this temperature to Kelvin. We can see that the temperature T required for the hot air balloon to have liftoff is 306.6370 Kelvin, or in other words, approximately 33.5 degrees Celsius. So in other words, we need to heat the hot air in the hot air balloon until it has a temperature of approximately 33.5 degrees Celsius, because that temperature is associated with a volume that is sufficient enough for the buoyant force acting on the balloon to equal the weight of the balloon and for liftoff to be achieved. Okay, so that should be it for this video. I really appreciate you watching. Thank you very much, and I will see you next time.